Thank you. I would like to thank the 4 organizers in their perseverance to make this happen. I'm very grateful and happy to be here. So I'm talking about non-selfadjoint Schroedinger operators. Some of you may have heard me speak about this topic before, where I showed some construction of potentials, non-real potentials, such that the Schroedinger operator exhibits crazy, wild spectral behavior. And now in this talk, I want to show you that we can bring some kind of order into our eigenvalue picture by generalizing Lieb-Thirring inequalities such that they also hold in the non-selfadjoint case. So I will show you again the crazy eigenvalue behavior and then show you how we can control it. And the setup is the following. So we have a Schroedinger operator in L2 of the whole RD. So our potential V is a real or complex valued function on the whole Euclidean space. And I do not really care about regularity. Let's just assume it's sufficiently regular. You can think of piecewise continuous functions. If we just look at the free Laplacian, I'm sure all of you know that then the spectrum is just the essential spectrum, and we get the non-negative real line. And now we add the potential, and we assume that the potential goes to 0 at infinity. So this is then a relatively compact perturbation, and the essential spectrum is the same. But now, in addition, we have discrete spectrum here. So isolated eigenvalues that are away from the central spectrum. There can be finitely many or infinitely many. If there are infinitely many and they accumulate somewhere, the accumulation point always needs to be in the central spectrum. And now I'm interested in where these eigenvalues can lie. In the selfadjoint case, of course, the discrete spectrum is always in the negative real line, and the only possible accumulation point is 0, the bottom of the central spectrum. But in the non-selfadjoint case, we can be in the right half plane. And now I would like to know what's the modulus of the eigenvalue. How can we somehow bound this, or maybe the modulus is the distance to 0, maybe better the distance to the central spectrum. And then if there are infinitely many eigenvalues, can we somehow find an accumulation rate to the central spectrum? In the selfadjoint case, you can do this using the Lieb-Thirring inequalities. If we now assume that V goes to 0 sufficiently fast, that we are in an LP space, where P is sufficiently large, depending on the dimension D, then there exists a constant, C dP, only depending on the dimension and the P from LP, such that now for all selfadjoint Schroedinger operators with real valued LP potentials, this eigenvalue power sum is bounded by this constant times the LP norm to the power P. In particular, as an even further lower bound, you can just pick one eigenvalue, and you get an individual eigenvalue bound that each eigenvalue in modulus is bounded by the LP norm. But now in the non-selfadjoint case, we can have eigenvalues in the right half plane, and they can accumulate to the central spectrum. And so the Lieb-Thirring inequalities do not hold in the non-selfadjoint case, because then what we add up here is not a 0 sum, because they accumulate at a non-zero point. Whereas if we can have such a phenomenon for an LP potential, the right-hand side is still finite, but the left-hand side is infinite. And indeed, we can have very crazy behavior. If we take P greater than the dimension plus 1/2, then there exists bounded LP potentials such that the supremum norm and the LP norm can be made arbitrarily small, and there are infinitely many discrete eigenvalues in the lower complex half plane that accumulate at every point of the central spectrum. So in particular, the eigenvalues are not bounded by the LP norm. And I proved this in 2017 for p greater than the dimension, and so d. And then with Jean-Claude Cunha, we could improve this and prove it also for lower p's as long as they are larger than this d plus 1 over 2. So now I would like to, before I generalize Lieb-Thirring inequalities, I want to talk a little bit about just individual eigenvalue bounds, because of obviously not even individual eigenvalue bounds hold in the non-selfadjoint case. So this is slightly easier to generalize the individual eigenvalue bound, and then I will come back to how to somehow modify the Lieb-Thirring inequalities to make them also hold in the non-selfadjoint case. Yes, then there are only finitely many by results of Pavlov. So in one dimension, this crazy behavior can happen only if p is greater than 1 in one dimension. And indeed, if p is equal to 1, the eigenvalues are nicely behaved. They are in a disk around 0. The modulus is bounded by the L1 norm. So this crazy behavior cannot happen. So in particular, exponentially decaying potentials will behave nicely. And then Lieb-Thirring and Safronov conjectured that also in higher dimensions, the modulus is bounded by the LP norm for a certain range of p. And this is not true for all of p. Rupert Funct proved that it's true for these p. And then with Jean-Claude, we proved that if you take p higher than this right-hand side, then this is not true, because for all epsilon greater than 0, we could construct an eigenvalue, 1 plus I epsilon, so slightly above the central spectrum, but arbitrarily close. A discrete eigenvalue, and the corresponding potential V epsilon goes to 0 as in P norm as epsilon goes to 0. So here this right-hand side goes to 0, but the eigenvalue approaches 1. So the left-hand side is 1 and the right-hand side goes to 0. So that's a contradiction. So this individual eigenvalue bound does not hold, and we need to find a different one. Fortunately, even before we found this counterexample, Rupert Funct proved a weaker version of an inequality. But now, instead of just taking the modulus, he also took the distance to the central spectrum. If your eigenvalue is in the left half plane, then the distance to the central spectrum is just the modulus. But if you're in the right half plane, then the distance is the imaginary part, which is smaller than the modulus. So if you replace some of the modulus by the distance to a central spectrum, then you get a weaker inequality. And he could prove that if you now take the distance to this power times the modulus to that power, then this is bounded by the LP norm to the power p. Now you can, maybe you wonder whether this distribution of these exponents is optimal. First of all, I should say that if you are in the self-adjoint case where all the eigenvalues are in the left half plane, or actually in the negative half line, then the distance is equal to the modulus. And if you add up these exponentials, these powers, then you get the classical result that the modulus to p minus d half is bounded by the LP norm, so you get the classical inequality. And throughout my talk, I will only present to you generalizations that somehow reproduce again the classical results if you plug in a real potential. So now you may wonder, or at least I wondered, whether this distribution of the exponents is optimal. You get a stronger inequality if you increase the power on the modulus and correspondingly decrease the power on the left by the same. But it turns out that what we have here in Funct's bound is optimal because in the example with Jean-Claude, the LP norm goes to 0 exactly in that order. And so if you would distribute it in a different way for a sharper inequality, you would get a contradiction. So this Rupert Funct's estimate is optimal. So I'm very happy with Rupert Funct's result. This is the optimal way somehow to characterize eigenvalues, individual eigenvalue bounds. And I was hoping that for Lieb-Thirring inequalities, one can find similar sharp generalizations that also reduce again to the classical results, but are somehow sharp. And I want to show you what I did now. So first, I give you a bit of background on what type of generalizations are known. So Funct, Lieb-Thirring, and Schroedinger proved a Lieb-Thirring type inequality that looks, if you look at it first glimpse, it looks exactly the same as the Lieb-Thirring inequality. But instead of taking the sum over all discrete eigenvalues, you take only the discrete eigenvalues in the left half plane. Then exactly the same inequality is true. And now if you want to add some of the eigenvalues in the right half plane, you have to exclude a sector around the real axis with semi-angle phi. And then you can sum over all of the eigenvalues outside of this sector, but you have to exclude this one. So this is what this inequality here says. And then the right-hand side, the constant in front of the potential, it now depends on this angle phi. And if you want to add more and more, if you want to include more and more of these eigenvalues, you have to make the phi smaller and smaller, but then your 1 over tangent blows up, which is an annoyance, as we would like to sum over all of them. Demuth, Hansmann and Katriel found a way to somehow integrate this previous inequality over the angle phi and get a new inequality where you now sum over all of the discrete eigenvalues. And I will show you the proof idea in a second because I improved it in the meantime. But what they end up with is, so again, something that depends not only on the modulus, but also on the distance to the central spectrum, which again, if you're in the self-adjoint case, the modulus and the distance are the same. So also this additional epsilon that we somehow seem to have, they cancel out and you just have the left-hand side of the classical Lieb-Thirring inequalities. And now here the constant also depends on this epsilon. And now for each epsilon sufficiently, arbitrarily small, you get such an inequality. And it's a sharper inequality, a better inequality if you take a smaller epsilon. So they were wondering if you set it equal to 0, whether it still holds. And then that would be somehow then the sharp estimate that we were hoping for. So they published this as an open problem. If you set epsilon to 0, whether such an inequality holds, or whether you can find a counterexample. Together with František Stampach, we found a counterexample. So it stayed interesting. So far in one dimension, we looked at an easy class of potentials. The easiest that I can think of that are still in LP. You just take a rectangular barrier. So characteristic function on, say, the interval -1, 1, and you multiply this by a constant, a purely imaginary constant here, I times t for t positive going to infinity. So we took the left-hand side and divided by the right-hand side, by the LP norm to the power p, and we proved that in the limit t to infinity, this is infinity. And using a numerical range argument, you can see that the imaginary parts of the eigenvalues are between 0 and t. It actually turns out, I will show you on the next slide, that the eigenvalues that I'm interested in, that I want to sum up, will be on the upper part of, on the upper boundary or near the upper boundary of this strip. They will have almost imaginary part I, or imaginary part t. So t is somehow not only a measure for the height of the potential, but also for the height of for the imaginary part of the eigenvalues that somehow make this inequality go wrong. And it turns out that this here goes to infinity at least as fast as logarithm of t. So later on, when I will show you a new Lieb-Thirring type inequality, you will see that I had to include some logarithmic term as well. So what I will do now is show you a proof idea of this result. And then I will give you a better Lieb-Thirring type inequality than the Demuth, Hansmann, Katriel result with their epsilon. And then I will show you that this is sharp by again using this class of potentials, but then the calculations are a bit more messy, and so I decided I mainly show you the proof of this, and then I will just tell you what will be different. So this is the proof of this is just straightforward, calculates the eigenfunctions and eigenvalues. So you want to solve this eigenvalue equation. Inside that interval, it's a cosine function, or I chose it to be a symmetric function, so it's a cosine function. And outside, it's an exponentially decaying function because that parameter k has or shall have a positive imaginary part. And then this constant in front just makes my function continuous, but we also need the derivative to be continuous, and therefore you see here we have a mu and a k. It turns out k and mu need to be related like this. And then outside of that interval, the potential is 0. So if we take the second derivative of this, we immediately get the eigenvalue, namely k squared. And inside the interval, we have here this it. This now needs to be the difference of these two squares, because the second derivative of this then has a minus mu squared coming out. So we have this inequality, and we can now take this inequality here and use that k is given in terms of mu. So we get an inequality, an equality we want to find now mu's that solve this equation. This quotient here shall be equal to IT, where t is fixed. And then the corresponding, we take solutions mu, then we check whether k given like this has positive imaginary part, and then the corresponding lambda will be an eigenvalue. And we want to find sufficiently many of such eigenvalues such that we get a lower bound that still goes to infinity. So we do not need to find all of the eigenvalues, but I will find sufficiently many, and I'm looking in the mu plane in a certain region. So I give myself a bound on the imaginary part. The imaginary part is in between these two lines that grow logarithmically in t, and the real part is bounded from above. So there is this line. So in this kind of strip, I'm finding my mu's, and I have some constants alpha, beta, gamma, positive. If you do a lot of ugly computations, you find that the solutions mu j are given like this. For each j, each integer in this region, I get a solution mu j. And then you can compute the corresponding eigenvalues. As I said, the imaginary part is almost t. So certainly uniformly in all of these j's, I can find the lower bound t over 2. And the modulus, is kind of the real part. The real part is much larger than the imaginary part. And we find an upper bound in this integer j. And now we are interested in this quotient here. We had the distance to the essential spectrum, which is the imaginary part because we are in the right half plane. And then we take here the square root of the modulus. So we take the square root of this square. So we just get a 1 over j. And now you can compare this sum by the integral over 1 over j over your variable. I hope you remember that this is the logarithm. So you have to evaluate the logarithm on this upper bound and lower bound of j. So you get the difference of the exponents, which is beta minus alpha, times the logarithm of t. And this red t to the p comes from the imaginary part to the p. And it turns out this is exactly the same order as the LP norm to the power p, and in the end we need to divide this sum by the LP norm to the power p, so this red thing will cancel out. And we see that we can't find a constant that bounds all this because this lower bound is going to infinity logarithmically in t. Okay, so we need to find a better Lieb-Thirring type inequality. Here it is. This looks slightly technical. Let me talk you through this. We have the same quotient as before that I said was not good enough. I can't bound if I just have this quotient. So I need another weight function, f, that somehow makes my behavior be nice if I'm near the real axis. So I need here this quotient, the distance to the essential spectrum divided by the modulus. This is always between 0 and 1, and at 0 is the difficult part if I'm near the essential spectrum. And then I need to take minus the logarithm of this quotient and then f of this function. And I wrote it in such a complicated way because I have some assumptions on this function f. This function shall be continuous and non-increasing. and it shall be an integrable function. So the integral from 0 to infinity of this function shall be finite. And then for each such weight function, I now get a Lieb-Thirring type inequality. And my constant on the right depends on this f. And there is a more explicit version. The constant depends on f in the following. We take the L1 norm plus the L infinity norm, the supremum norm, because it's a decaying or non-increasing function, so the maximum is attained at 0. And this is a generalization of the Demuth Hansmann and Katriel bound with their epsilon, because if you plug in as weight function this exponentially decaying function with parameter epsilon, you recover exactly their bound. But of course, there are other L1 functions that decay slower than exponentially. And then for each of these new weight functions f, you get a better estimate than their bound, which until now was somehow the best that was known. So here are a few examples of functions f that satisfy my assumptions. So we need it to be non-increasing and integrable. 1 over s is not yet integrable, but 1 over s to the power 1 plus epsilon. Or instead of the additional s to the epsilon, you take logarithm of s to the 1 plus epsilon, or s times log s times iterated logarithm to the power 1 plus epsilon, and so on. There is unfortunately no best possible function, because you can always iterate it and you get an even slower function. And whenever you set epsilon to 0, it's no longer integrable. But all of these classes of weight functions give better inequalities. So now I want to prove this result. Give you a proof idea. So I want to sum over all of the discrete eigenvalues. I do the following. I first sum over all of the eigenvalues that are outside this sector S, where phi is pi over 4. And we know that they behave nicely by the Funct-Lieb-Thirring inequality, which said something like written here. It's bounded by 1 plus 1 over the tangent of phi, which I now just wrote as t, and then to power p, and then times the LP norm to the power p. So we get, so first, if we are in this, outside this sector S, the discrete eigenvalues satisfy this inequality. The distance to the essential spectrum is bounded by the modulus, so we can just take the modulus for all of the powers. And then the function f is bounded by its supremum. And so outside the sector, we just get, oops, what did I do? We just get constants, and then f of 0, which is in this constant here in the claim, times the LP norm to the power p. So outside the sector, this is okay, but now inside the sector is more difficult. So we now take the lambdas inside the sector, but that are still outside a smaller sector with now a smaller phi. And I write t as tangent of phi. So we have this inequality from Funct-Lieb-Thirring And I mainly don't like this 1 over t. I do not care too much about this 1 because that's smaller. So I can just take another 1 over t. So I get this bound here. And now we have this bound is true for all t's between 0 and 1. And it's also true if you multiply both sides by something non-negative. So I just choose now, I make a clever choice of function with which I multiply, and then I integrate over t, and you will see that I end up with all of the discrete eigenvalues inside that sector S. My clever choice, which is just a modification of the Demuth, Hansmann and Katriel result, but I kept the they took a particular choice of f, and I just keep here my general function f. So I multiply both sides by this function. Fortunately, now this t to the minus p singularity is killed by this t to the p. And I have another t to the minus 1, because then when I integrate, I want to substitute what I have here inside f. And then the derivative of logarithm is 1 over t. So this kills this additional 1 over t. So on the right-hand side, after I have multiplied by this and integrated over 0, 1, I just get this wonderful integral, f of s, which, so then we shouldn't forget that we also have this LP norm to the power p. So in the end, we do get here this right-hand side. We have a constant times LP norm to the power p. And where is it? Here. We have this integral that appears in the constant. So all I have to do now is to convince you that if I do the same on the left-hand side, I multiply by this function and I integrate over this interval, that I get this thing here if I take all of the discrete eigenvalues in my sector S. So I do this here. On the left-hand side, we had such a sum, and then I multiply and I integrate. Now I change integration and summation, because fortunately we have an upper bound on t now. If I take the real part on the other side, t is actually then bounded from above. We do not go all the way up to 1, but up to there, which is smaller or equal to 1. And then this modulus did not depend on t, so I can take it outside. And so we have the sum over all discrete eigenvalues in S times this modulus times this integral here that also depends on lambda. So this I now have to compute, or it's enough to find the lower bound. So I do again the same. I substitute what I have here, S is minus logarithm of t. And now I have to somehow evaluate this integral, which is slightly complicated. I tried integration by parts because I know how to integrate exponential functions. But then you get a derivative in f. And then I used an assumption that I had to introduce artificially, that the derivative and the function itself satisfy this inequality. This somehow corresponds that it doesn't go to 0 in a very wild, wavy behavior. If we assume for a second only that the function f is that nice, then you can evaluate it nicely and you get this lower bound. And now if you multiply again by what you had here, you indeed end up with this left-hand side. But then slightly annoying and technical part of the proof was then to somehow not having to write this assumption in the theorem. So if I started with an arbitrary function that satisfies my assumptions, I found a slightly larger function that does satisfy this inequality, and somehow its L norm and L infinity norm was equivalent, such that I did not have to write this assumption in the theorem. So this is this improved Lieb-Thirring type inequality, and now I want to show you that this is sharp. It's sharp in the following sense. If I just drop the assumption that my function f is integrable, then such a Lieb-Thirring type inequality cannot hold. Because the left-hand side divided by the right-hand side, if I make a clever choice of potentials, then you can't find an upper bound, a constant by which it's bounded. And we proved this so far in one dimension. And the class of functions is again the same as before, this complex rectangular barrier. Well, the computations are the same. I just allow a few more eigenvalues to be counted as before, because before I had these constants alpha and beta that are positive, and now my lower bound needs to go to 0. So I have an alpha of t because I want to add some more eigenvalues. So then in the end, if I add up the things, I get here this integer j, and its lower bound is this alpha of t. So this then corresponds to, okay, if I now compute the integral, I have this integral of the function f that is not integrable. The upper bound, as t goes to infinity, but unfortunately the lower bound goes to infinity as well. This epsilon is e to the minus alpha of t, which is throughout my computation always my error bound, and it has to go to 0. But I can choose it to I can choose alpha in such a way that this epsilon goes to 0 arbitrarily slowly. It just has to go to 0, and then I just take epsilon to go to 0 so slowly that okay, this lower bound still goes to plus infinity, but so slowly that still this integral goes to plus infinity. And so this proves that this quotient can be unbounded for this particular choice of functions. And therefore, we cannot drop the assumption that f has to be integrable. And in that sense, my new Lieb-Thirring type inequalities are sharp. Some open problems still. And here I probably should go back to here. In my new theorem, in my new Lieb-Thirring type inequalities, so I used this Funct-Lieb-Thirring result, and they always had the assumption that p is greater than d over 2 plus 1, which is slightly larger than d over 2. Usually we look at Lieb-Thirring type inequalities starting from d over 2 in higher dimensions. And in one dimension we start at 1. But so because I need their result, if their result does not hold for smaller p's, then maybe my result also doesn't hold for smaller p's. So I'm wondering in higher dimensions what's happening if I'm below the 3 over 2 and in higher dimensions d over 2 plus 1. My new inequalities do not apply there. So in particular, yeah, it could be that the Demuth Hansmann and Katriel bound is true because so far I disproved, or we disproved it only in one dimension. So in higher dimensions, it could be that their bound is optimal, but I don't think so. And if this is not true, then hopefully my Lieb-Thirring type inequalities are optimal. So probably the same counterexample that will prove that this epsilon equal to 0 bound is not true, will then also prove that my Lieb-Thirring type inequalities are sharp. Okay, that's everything for now. Here are some references. Thank you for your attention.